This is a lecture on implementation and coding. First thing I want to say, I will have said this in class on one of the earlier lectures where we talk about the place of 428 in the curriculum, is that it's sort of one of the things I don't care as much about in this class. Obviously, you have to do it. You have to code. You have to implement or you didn't build anything. But we talk a lot about that, I think, at 240 and 340, and there's some places where this gets handled, a little more deeply. For me, this is more just kind of my review, my take on stuff you really should already have had a handle on, in your previous time. And this is leveraged heavily from McConnell's book, Code Complete, which I think last time I checked was required in 240, maybe 340 as well. And it's a good book, a really huge, voluminous encyclopedic effort by McConnell. I think it was actually McConnell's first book, but quite good. So here are the issues, why construction is important. And this is just going to be the big no-dust slide. It's the pivotal activity. You have to do it. The productivity becomes important from a programmer productivity perspective. And often when we start talking about what the product is, the source code is all we maybe really have. And it's the only phase that's kind of guaranteed to be done. That's not strictly true, right? Because there are a lot of companies and situations, organizations, where the planning is the only guaranteed to be done, because after they do the planning, they never actually pull the trigger. So maybe that's not strictly true. There are probably more companies where coding happens and nothing else than there are companies where other stuff happens and coding doesn't happen. Eventually, you have to build some stuff, or you really aren't a development organization. That's kind of the big no-duh. The other thing I want to say, though, we've talked about orders of ignorance by now in the lectures in class, is that software construction is also the most outsourceable chunk. So if your only value add is that you're a hot coder, you're outsourceable. You might be worth something because you're a hot coder, but in reality, you're outsourceable. This is not strictly the phase of the operation where the greatest innovation happens. I think that's a really important takeaway, because a lot of times we get so stoked about what a great code slinger I am that you forget the fact that I could hire 5 of you in another developing country and get the product built. And really, it's other stuff where the greatest value add actually happens. So this is McConnell. I'm gonna walk over to the screen. Nothing really dramatic. This is more just to think through and articulate. Okay, building a routine. We have so this is not rocket science, and it will not be on the exam. It's just an opportunity to tear it apart, tease it apart a little bit, and articulate. So we're going to do some design. And our next step is to check that design. If we find goofiness, we go back, we're going to design it a little more, and then we go into this coding, and then we're going to check the code somehow, and then we might go back to design. And if you look at this, all this really is a kind of a modified waterfall cycle, just dealing specifically with a subroutine, with a small module, and articulate it a little bit more carefully. That's really all this says. There's another issue. I'm not going to beat on this much. I just want you to be aware that there is an issue of design notations. They'll sometimes call them program design languages, PDLs. You can have everything from English language descriptions to particular kinds of drawings. You can have things that are kind of formalized and specified, like UML. You can have, I've done a lot of design in my career without any, pre-UML, before UML even existed. And you always figure out a way to draw a picture. And the better you can draw a picture, the more able you are to express what it is you're trying to say. And the communication becomes one of the biggest issues when you start talking about design notations. So they can be very formal, very informal. And the last part, depending on the complexity of the routine that you're building, it may be more or less important. If it's really complex or really tricky or very, very important or safety critical, mission critical, then maybe it becomes really critical to specify in a really detailed, articulate way. Another example where I think it comes up, so I did a lot of work in data communications, wireless data communications, infrared stuff, ERDA, Bluetooth. Bluetooth, not infrared, but radio, but ERDA is infrared. And what you find when you go into the documentations for, say, ERDA or Bluetooth is you'll find in certain technical areas page after page after page with like state machine diagrams, because you're dealing with data communications, right? And you've got to have a situation where I need to be able to say that in our interaction, we move through a certain state, and then from that state, the following things can happen. That has to be absolutely, specified, concretely, because you've got devices that everybody's going to build around the world, and you're going to basically buy a headset and just pair it to your phone, and maybe it's the first time that that's actually been tested in that exact configuration. So if they're each exactly true to the spec, then you're going to be okay. And the spec has to be absolutely nailed down. So I've seen massive elaborate state machines or other kinds of diagrams that try to illustrate in really concrete terms what you do at this point when this happens and that happens. So from my experience, data communications winds up being an area where a lot of this sort of thing happens. So I'm actually going to fly through this fairly quickly, and I want you to kind of look at it. But all I'm going to really try to do is just identify some of the highlights while you look at the slide, okay? So the first slide, I think I've got 3 slides on designing the routine. Check the prerequisites. Make sure that this thing fits. Are there any other specs that relate that you need to be looking at? Make sure you actually understand the problem. It's so common to jump in. This is also true in your dating and marriage relationships when you jump in before you actually know what the other person's saying. Probably true with roommates, I suppose. I don't know if you're not in marital bliss. Naming becomes an interesting question with clear and unambiguous names. And the last bullet I think is important. If you can't come up with a succinct name, you don't understand what this thing does. And that I think is really critical. And it's true in a lot of fields. It's true in research when it comes to like the title of your paper. If you know what the title of your paper is and you can articulate it, you understand what you're doing. I've seen a lot of mushy titles because they really weren't sure what they were doing with it. The second one becomes figuring out how you're going to test it. And this is probably one of those issues that's largely ignored. Just because we don't necessarily think about testing. We don't make you think about testing as much as we should in this department. Think about efficiency. So you're thinking about that in the first place. And I think with respect to that, think about scalability. A lot of times we think about efficiency of it's really fast when n equals 1 or when n equals 2, but when n equals 1,000,000, did you code up something that is now just creaming you from a performance perspective? Researching algorithms and data structures. Now it's time to do some homework. If there's somebody else that solved this problem, you don't need to. Okay, and then the last slide on designing, documenting your design. You can throw it in the header somewhere, but we have insights, and if we don't write them down right in the moment, we lose them. Think about the data. The data structures vary, obviously. And again, checking the design doc, at least review the document yourself. And keep in mind, too, and we need to say this, depending upon the organization you're working in, this may be completely irrelevant or absolutely lacking in sufficient detail. Some companies, if you're going to go to work for NASA, you're going to have a very, very large document set, and you're going to work and live in documents. You have to, because there are so many people, the projects are so large, the criticality is so high, the money investment is so high, and safety critical. If you're, you and a buddy, right, Ted in the shed, you're not going to probably write all this stuff down, or you're going to just drop it into a header, throw your cryptic notes in, and then just start coding. And those are both okay, and anything else in between on the spectrum. The only real issue is what is it that you need to do the job. And it relates to the thing I said in the process lecture, that you need as much process as you need to be effective, and no more and no less. Well, the same thing is true here, and this really relates to process. You need as much documentation as you need to be successful. If you have too much, you're bogging down, burning all your time on doc. But in some organizations, you have to because of the other organizational needs. Whereas in other situations, your best thing to do is just start coding and just fly by the seat of your pants. Maybe that's your best process. And you've got to come to grips with that. Okay, coding the routine. Again, I think I've got 2 slides on coding the routine. Again, not real big deal. Writing the declaration, turning the design. I wanted to say the second bullet to me is kind of an important one, and I just want to say this. This is supplemental to 240 and 340. I found, as a professional software engineer in the 80s and the 90s, the way that I would tend to do it is I would tend to build sort of a stubbed out system where there was no real working code. Or maybe I was putting some kind of I/O, either a little print statement, whether it's printf or cout or some other sort of write line, if you want to go back to Pascal or Modula, something that would suggest I got here, I'm in this module, that kind of thing. I'm in the constructor, I'm this, I'm that. And then build a system that has no functionality but only a structure. And then you test it. So that you know that if this data comes, or if you press this keystroke, or if this happens, that happens, but your code's not doing anything. And then you roll back in and you begin to flesh out each module. And it's a really great way to do it. The idea would be that you're doing it kind of incrementally, and you know that it works as you go. There's no put the whole thing together and send it off the runway and watch the whole thing explode. So you know that the main works. And then even as you're building these little branches, even little, I'm going to spin off a little object, spin off another one here, do this thing here, send a message there. All of it is kind of empty, but you test and you assure that you know that it works. And every time you add another 20, 30 lines of code, you stop and you make sure that little bit of code now works. So you're constantly, it's kind of like constantly integration testing. There are situations that you can get into, obviously, where you've got, maybe it's like 500 lines or 1,000 lines, and there's so much interdependency, right, that until the whole thing's all done, you can't really test it because of interdependencies. At that point, you have to stop and do a little bit more of an actual little unit test on that. But most of the time, you can actually get by. And so I just like this idea. And then when you begin to design, once you have the structure built, then you just throw in comments. Do this, do this, do this, do this, do that. Beware of this, beware of that. And then go to the next one. You fill it in with comments, and then you start fleshing out the code beneath each little block comment, each little header comment. I just think that's a great way. I don't know if they teach us. I don't know if we teach this in the department. We ought to. I just think, in my experience, it was just the safest way to build code, because every time I took a step, I didn't have to stop and look backwards. I typically never encountered bugs later in the process because I was more meticulous as I built it. Maybe I was a little slower, and sometimes you can get this delusion that you're just kicking it, but really you're just banging out code, and you're gonna be basically chasing your tail forever. Okay, the second one, check the code informally, kind of basically little code review, and I mentioned this, testing each new edition. And whatever, clean up the leftovers, are the inputs and outputs accounted for, check the data, check stuff, repeat as necessary. This is not rocket science, and I think that probably in 240 and 340, you've had enough of this probably. The other thing with respect to checking the code, I think I've got 2 slides here. Mentally check the routine for errors. It's a process of thinking through it. One of the advantages, by the way, of pair programming is that you have a second pair of eyes constantly. It's like a constant visual inspection. I mean, it's one thing for it to compile, that's good, it needs to compile. And when it doesn't compile, you go looking for syntax errors. But it doesn't help you with logic errors, right? When you got somebody looking over your shoulder and you're doing pair programming, you have a constant review like, hey, wait, hang on, that looks weird over there, why is that? And then you stop and you talk about it, maybe it's a problem or maybe it's not, Compiling, set the warnings to the pickiest level possible. And if you have warnings, I mean, errors obviously is not going to go. But if you have warnings, you absolutely have to understand why that warning was generated. Because I've seen a lot of situations where you're just kind of rolling and you got all these warnings, but you ignore them. And then you're having all these problems, you don't know why. So it doesn't violate the syntax, but there's something logically that the compiler's nervous about. If you ignore the warning, you do so knowing full well what the warning was and why it's okay. If you don't have that, you're really operating in a danger zone. And then, warnings often suggest low-quality code, and I think that's true. Typically, there are ways to be more explicit within the context of the specific language so that you do something more explicit rather than implicit, so that the warning, usually the compiler's like, this is a little ambiguous. I have my own default way of dealing with this. I'm going to, you've taken a long piece of something and you're trying to shove it in something smaller, and I can truncate that and I can put it over here, in this smaller little structure, but it makes me a little nervous, and maybe you know what you're doing, or maybe you're losing data, in the high order bits of this long or something. And a lot more meticulous to do checks, like check this part to make sure it actually is empty and can be truncated, or that you understand the logic behind that, et cetera. So, we just save a lot of pain if we do that. Okay, the second, let's see, the second slide on this, using debugging and tools, kind of the big no-duh, removing errors. If you have a lot of bugs, you probably have lousy design, and this I think is really important. If you find yourself chasing your tail, make a tweak, you fix a bug and create another one, fix that one, recreate the first one. You ever done it? You're like chasing your tail, right? When you find that, typically you've got bad design. So stop thinking about the code and double back and start looking at your overall design, or even in some cases, your understanding of the fundamental problem. You need to have a clearly, in your mind, clearly articulated solution to the problem. And you can't just have a vague notion and then start coding it and say, I'll figure out the solution as I'm going. If it's at all tricky, you could just chase your tail indefinitely. If you just stop, work it on a whiteboard or work it on a piece of paper, and make sure you absolutely know precisely what it is you're doing. And the specific, you know that your solution works because you worked it out on paper on the board. Coding that's going to be like 15 minutes or a finite amount of time. And the only projects that I never finished in my undergrad were ones that when I look back on it, I was trying to code to a solution that I didn't understand. I thought I understood it. I start coding up and I'm doing whatever. I did this like crazy doubly linked list in assembly language in like a second semester course at the University of Iowa in like whatever it was, 83 or something. And I was up for a couple of days, and as I think about it, if I had just taken even a half a day, even 6 or 8 hours, and just walked through the solution so that I deeply understood it, I probably could have coded it in another hour. And I was up for like 3 days because I couldn't, you get that kind of psycho thing where you feel like I'm on the cusp, I think I'm almost there, it mostly works, it only fails in this one little thing, and I somehow can feel like I can go down there and fix that one thing. The problem is the whole structure's wrong. And so when you go down and do that one thing, it has this unintended side effect. So, that's just one of the huge things. You've got to absolutely have a crystal clear understanding. And this last bullet, you cannot operate in the realm of superstition at this point. I think that's just absolutely critical. If you don't know why it works, you're not done. Now, I understand you need to pass it off, you got to get on to other sides. But in the real world, in the actual professional software world, you cannot operate in the realm of superstition with a working product. You have to know that it works and exactly why it works. You have to grok it at that level. And really, even if it appears to work, if you don't know why, you're really not done. And the other one was beware self-correcting code, because it will also self-break later on. And all that really happened is that there's some other condition, some other circumstance, some other data that overflows and trashes you, and it just didn't happen to overflow this time. Now it works, and then later on it's going to overflow, it's going to trash you. Beware self-correcting code. Okay, so we're going to talk a little bit more about coding stuff. High-quality routines. These are characteristics of what I would consider to be a high-quality routine. It was included for a good reason. That's kind of like, again, most of this just feels like really no duh. By now, seniors for the most part, they have good routine names, they have strong cohesion, and they have weak coupling, okay, or loose coupling. They have a reasonable length. They employ defensive programming. When we talk about good method names, a strong verb followed by an object like print report. You have the object-oriented method, right, that presumes the object, like report.print. Avoid meaning, really wishy-washy verbs like process input. It's just not specific enough. Keep in mind, too, this is the biggest mystery. In another lecture, we talk about maintenance. And the biggest thing I think we do poorly, well, maybe not the biggest, but a big one, that I think we do poorly in our department, and probably in most CS departments, is we really don't maintain other people's code. You don't read other people's code. When you do read other people's code, we typically call that cheating, right? Because you're not supposed to look at other people's code. And, but in the real world, you read people's code all the time. And so if you're reading somebody's code and there's like 500 varieties of input, and you got a routine called process input, and you don't know what you're doing or why you're doing it, and you have to maintain it, which means you have to tweak it or change it or, you know, fix a bug in it. The ability of somebody else to come in and read your code who isn't you. So you just have to understand that writing code, for the most part, code is not written for yourself. Code is written for somebody, for the compiler to read and for somebody else to read. And I think it's a really important issue. Make the routines as long as, you know, the names as long as they need. Some say as many as 35 characters is fine. I think 15 to 20 is not too long. So, you know, this becomes an interesting question. How long can a method be? Back in the 70s, there was kind of a rule of thumb, you know, that 50 lines was the IBM rule. And I just think that's, I don't think it's reasonable, you know, in a modern era, that a routine or a method, you know, is 50 lines. TRW standard was 2 pages, you know, and you got to figure out what the balance is, right? I did one time work on code at Novell where I maintained, which means I had to change, a 1,000 line switch statement. And it was trying to embody a state machine. It was a horrible architecture. Really, really horrible. I mean, the pervasiveness of the side effects in this system, it was just horribly designed. I think by the time you get to a 1,000 line switch statement, probably aren't looking at a pretty decent design. Once you get above, some studies suggest that once you get above about 500 lines, then the errors start to increase. And I don't know if they increase linearly or you know, non-linearly. I suspect they increase non-linearly. You know, I think that a code with 1,000 lines has got to be more than twice as susceptible to bugs. I'm pretty sure it's non-linear. Smaller modules, easy to fix. The other problem, though, if you look at the trade-offs, if you got smaller methods, you also have more methods, which means you need more glue code to interact, to interact with the methods, to stick all the methods together, and that therefore creates greater object complexity. And so there's kind of a trade-off between one big monolithic thing, which has a relative simple interface, but a lot of complexity internal, or breaking up all into modular chunks, and then all of your complexity is in the interactions. And frankly, it's a trade-off. It's not like there's some absolute answer to that. You have to look at the system. One other thing I wanted to say, if you remember from 404 we watched, it was probably Revolution OS where they interviewed Richard Stallman. He actually talked this issue, not strictly about method length, but about monolithic versus distributed sorts of architectures. Turned out to be the linchpin for why they used Linux as the kernel in the GNU system. I don't know if you remember that, but he went for, I think, a very complex and beautiful and elegant whatever, but it was just really tricky. And then Linux was kind of more monolithic in the architecture, which was less elegant in some respects, but more containable. But there's just a trade-off. That's really all I'm trying to say. What about with language? Okay, I got a couple of quotes here. One, Edward Sapir was a linguist for the 1920s. This is actually a quote that I used in my dissertation. So this is Sapir. Languages differ not only in how they build their sentences, but also in how they break down nature to secure the elements to put in those sentences. Language and our thought grooves are inextricably interrelated, are in a sense one and the same. Now this is the foundation of what became known as the Sapir-Whorf hypothesis. Sapir had a student by the name of Benjamin Whorf. He later went on to a career on the Enterprise. He was a Klingon. And actually, he was the grandfather of Commander Worf, was Benjamin Worf. And what he's really trying to say, the Sapir-Whorf hypothesis is basically that our language influences our thoughts, that we think within the context of language, and there are kind of hard and soft variants. Some that would say, if my language doesn't possess the ability to express it, I can't think it. And I don't think that's strictly true, because there are times when we have a concept and we go create a word to stick to the concept once we create a concept, like a linked list or some computational structure, or But we often find ourselves borrowing words, right, from other things. But there's an interesting question. So there were studies. When was it? Within the last 10 years, there was a study, anthropological study of a tribe. I don't know where they were. Aboriginal tribe. I'm going to say Brazil. Not sure. Amazon. But the idea was that in this culture, their language only included the numerical concepts of 0, 1, and many. So their language did not have a counting system. Once you were past 1, you were at many. And they did studies to see if these people could differentiate like 7 and 8 things, and they couldn't. 10 versus 15, 20 versus 40. Could they tell? And I don't know exactly what the methods were that they used to study it, but this would be an example of you miss things because of your language, and you see certain things because of your language. So when you start talking about programming languages, the same idea relates. Alan Perlis in 1982 said, a language that doesn't affect the way you think about programming is not worth knowing. And the point simply is that every language influences how we solve problems. And this was actually relates very strongly to my dissertation at Oregon State, which dealt with multi-paradigm design. How do you design within the context of different programming languages? What are the cognitive processes? So this whole language thing, I want to give you a little bit of a tour. So this is 20 years ago. It was a little confusing in more of a straightforward way. Maybe I'm going to go 25. I think I need to update my slide. It's probably not 25. Time keeps shifting. But 25 years ago, these were the languages. Assembler. So what we had basically was all of these languages are imperative, okay, which means they're procedural. They're not, in other words, the fundamental idea of how you do it, a procedural language is like the Betty Crocker cookbook, right? Take a bowl, put the dry ingredients in. This much of this, the salt and the flour and the baking powder, I don't know, the dry ingredients. And then in this other bowl, put the eggs and the shortening or whatever, right? And then and it's side effects, because once you throw these dry ingredients together, you can't separate them back out. So there are these side effects. And then at some point when you're all done, you bake it, and you just walk through the instructions. And it's basically, that's all procedural programming is. Betty Crocker cookbook, okay? Or an arbitrary other cookbook that's not Betty Crocker. So, understand that these are all procedural. And then the only real issue was the abstraction. So how close do you? So you have like, if assembler was like 1, then C was about 2.5, meaning that you had the representational power. You could kind of embody about 2.5 assembly statements in a single line of C. 3 for Fortran, 3.5 for Pascal, 4.5 for Ada, 5 for BASIC, etc. Okay, and that was the complexity. That's what you had to deal with. So C for operating systems and programming languages, assembler for core OS, Fortran for scientific computing, Pascal for education, Ada for military, BASIC for hobbyists. I mean, it was like, that was kind of the breakdown, okay, about 25 years ago. So about 15 years ago, and I think I really do need to update these. I apologize. I think it's really more like 15 now. The things began to get a little more confusing because now we had, in addition to imperative, which we pretty much reduced down to C and assembler in the imperative domain. All the other languages still exist. Ada still existed. I mean, Ada wasn't strictly imperative, okay, but Fortran still exists, COBOL still exists, etc. But for the most part, we began to think of imperative as kind of C and assembler. And then we picked up, and then object-oriented kind of came upon the scene, C++ and Java, and then functional programming showed up, which was primarily Lisp. And then logic programming, well, there were a lot of functional languages, but Lisp is the one that everybody knows. And logic programming, which is primarily Prolog, okay? So what you had was kind of a clear delineation between these paradigms. And again, read my dissertation. I kind of dealt with these 4 paradigms, which 15 years ago was the programming language landscape for the most part. And it turns out that the way you break down problems in these paradigms is different. Here's an example. If somebody, so when I was a student here and I lived on 500 East, like everybody does, I was at 269 North 500 East. Now, if you were to ask me how to get to my house, and I know that you live in Provo, you're not going to ask me, you're going to ask me what's your address. The first thing you're going to ask me is what's your address. I'm going to say 269 North 500 East, Provo. I might even clarify and say, yeah, that's in the student ghetto just south of campus, if there's any confusion, okay? At that point, we're done, right? Why is that? Because you had essentially a declarative, and I'm not really getting deeply into this in the lecture, but we have kind of a spectrum between imperative and declarative languages. Imperative, I'm going to tell you exactly what to do. Declarative, I'm just going to declare to you the constraints, and that gives you enough information to figure out the rest of it. So when I say I'm on 500 East at this address, that is a declarative solution, and you know the algorithm because you understand the grid system here in Utah, and you can go figure it out. But when you go, it actually freaked me out when I went to Corvallis to do my PhD, and I mean, I didn't grow up here, but I'd been away from non-Utah for a while at that point. And I go to Corvallis, and I'm just like, yeah, you know, I'd be going to somebody's house, or I'm going to go home teaching or something, and they would say, before even telling me the address, they would say, yeah, let me tell you how to get there. And I was just like, my first reaction was, oh, just give me the address. You know, because they knew that the address wouldn't help me. Arbitrary random number, arbitrary, you know, tree name, street, or northeast. There was a little bit of a quadrant, northeast, northwest, southeast, southwest, that would tell you what quadrant of town you were in at least. That was helpful. Because they knew that they needed a more imperative solution. So the whole point is simply that the way you deal with the world is impacted by the languages that you use, the way that you think about it. And when you deal with programming languages, there's a different way of thinking about programming and problem solving when you're in these different paradigms. And that's why, for me, I cut my teeth with BASIC, actually, back in the 70s. And so I cut my teeth with BASIC in the 70s, and then I learned Pascal at the University of Iowa, and an assembly language. And really back then, in the early 80s, it was kind of, you know, it was just a sequence of these imperative programs. And C showed up. You know, in Pascal, the C was a bit of a shift, but really, the problem solving didn't really change. People of my generation typically struggle to figure out this whole object-oriented thing because it was just a different way of breaking stuff down, a different way of conceptualizing design. Your generation has a harder time doubling back and taking wherever it is that they teach you the C in the assembly class. You freak out about C. I got no problem with C. I could, you know, I'm really rusty, but I could drop in and be a professional C programmer again, no problem. But I've always struggled, frankly, even though I taught 240, I've always struggled a little bit with the paradigm of object-oriented. And that's just true. That's just the way it works. And wherever you cut your teeth when you learn to program, you think of it as programming, and you don't realize that there were prior paradigms and future and other paradigms, and they're going to be hard for you. And you become what I call paradigmatically challenged, which simply means that having cut your teeth in a certain paradigm, it's hard to transition. And I don't think there's any real great way around that. Cognitively, it's just a bit of a struggle. Now here's today. This isn't even probably remotely accurate, but I've now got, if you look over there, we still have imperative. We still have object-oriented. Some, like Smalltalk, made a little bit of a resurgence. We now have what we might think of as web-oriented. In fact, I don't even have PHP on here, which absolutely needs to go on there. TickleTK, Perl, Python, scripting languages, right? So we have a web-oriented thing. Database languages like Delphi, which is kind of Pascal-based, or just simply SQL, you know, and it's in its many variants. GUI-oriented like Visual Basic, Visual C++, multi-paradigm-ish languages like C#, and Scheme. And there may be some purists, you know, that are going to roll in and argue with my taxonomy a little bit. Fine. You know, all it does is just reiterate my point. And then format-oriented, which are totally declarative. Those are not procedural at all. I mean, is HTML an actual language? It's hypertext markup language, but it violates our sensibilities because we think of a language as something that tells it not just what to do, but how to do it. You know, because there's always, even object-oriented programming, inside the methods, it's imperative. Inside those methods of C++ or Java, it looks like C. It's more the wrapper. Object-oriented has more to do with the wrapper than the actual specific code. And I'm not saying it's exclusive. I'm just saying it's more about the wrapper. Okay? So when you start talking about HTML or XML, these are not procedural at all. These are just simply saying, here's a set of requirements, right? I mean, I think of HTML as a requirements documentation language, because another system, namely a web browser, looks through the requirements and goes, oh, you want a title and you'd like the title centered in this font of this color. Oh, okay, but that's not instructions, that's a set of requirements. And I'd like this text to be displayed over here, and I'd like this to be over here, right? But now what do? Now we bring in, and I notice I also don't have up here, I haven't updated this in a little while, JavaScript is not in there, which is now suddenly a procedural and kind of imperative-ish thing that we drop into a web-oriented environment, but it interacts and interfaces with the format-oriented stuff. So I'm just saying, it's just a confusing world. You guys are growing up in a world. When I was a student, I would do the Language of the Month class. Through 3:30 used to be kind of Language of the Month. And I think at some level that's not a bad thing. You know, and we wrote code in, what did we do? We did Lisp and Prolog and APL and Forth. Forth was a stack-oriented language. The architecture was stack-based, like reverse Polish notation on an HP calculator. And APL was sort of like a matrix manipulation-oriented language with Greek letters instead of function names. And bizarre, right? And then we did C for the very first time, actually, in that class. So every one of these languages sort of partook of a different paradigm, and it helped to kind of orient you to the fact there are these other ways. And then you ignored all that, and you put them on your resume because you had at least written one program, and then you basically just went back to writing C. These days, you guys actually know HTML and XML and JavaScript and C++ and Java and C and assembler and, you know, in many cases, Python or Ruby or, you know, and SQL and C# and Scheme. And you're not just like tacking them on your resume. You're going to actually use them. Not all of them, but there's quite a few of those that you're really going to actually use. That's a really different programming world than the one I grew up in. It's dramatically different. And so, you know, I just think that, to me, it's kind of exciting because it's not like we're running around fragmenting our brains and losing productivity. I think what's happening is we're finally getting, it's kind of like when cars were first invented, there was just one car. It was the Ford, and it was the Model A. Was it Model A the first one? I think it was, Model A. Model T was later, I think. It was a Model A, and it was black. And that was it. That was automobiles. And today we have a little motor scooter, we have a bicycle and a skateboard, and a dump truck, and a pickup truck, and a station wagon, and a minivan. You know, why do we have all these vehicles? The fundamental notion of transportation isn't that different, but they just meet different needs. They serve different purposes. So there's a market for all of them. And in my house, I have a couple little commuter cars, a motorcycle, and a 15-passenger van. And a little trailer I can hook onto the back of the big van, you know, a little black utility trailer. So, you know, in our actual, when we're really programming in a live world, it's not unusual at all now, in this generation, to have a mastery of as many as 5 or 10. And by master, I mean a working fluency that you're like, yeah, no problem. I just threw together some Perl scripts, or I just threw together some, you know, some whatever. You know, and you know, knowing things like PHP or C# or whatever, you know, very standard stuff in this generation, which is actually kind of cool. So what I thought I would do is throw down a little Hello World tour. I need to update this again probably, but just, you know, check this out. So, and I'm not going to go through this deeply. I just want you to look at each one of these kind of as they pass. This is assembler. This is x86 assembler. Okay, the original sort of, you know, 8086. Anyway, just check that out. You got the little title, the little comments, the hello message, DB, hello world. Boy, I sure miss programming in assembly. Just, it's amazing. Here's Fortran. Those are your comments up at the top. And you've got, this is actually going to write it 10 times. And then you've got your little format instruction. And then here's Pascal with the write line. Interestingly, I didn't really like WriteLine. I thought WriteLine was horribly inefficient. I loved printf in C, loved printf, because of all the power you could put into one sentence, one line. And then C++ shows up and we have cout. And in my mind, cout is basically WriteLine, and I don't like it. So there's Pascal. Here's Lisp. Somebody once said Lisp is short for lots of insipid and stupid parentheses. Programmer cognition, comprehension, a little tough with Lisp. These are all just hello world. There's C. This is an infinite loop printing hello world as a printf. Here's Java, again, an infinite loop. Got just a couple more. Here's Python, and the Python guys are like, yeah, that's what I'm talking about, And here's Scheme. But I mean, it just, again, and they're actually not, this is from a Hello World project, ACM's Hello World project. Unfortunately, they're not all doing precisely the same thing. Some are printing it one time, some are doing it forever, 10 times, whatever. But just to try to just illustrate this idea that our languages just do different things. So the other thing that happens is every language has its own style, right? There's good style, bad style within every language, and you got to come to grips with what that is. We're kind of focusing on Java and C++, which is still the bulk of professional code and relevant to our curriculum. But the reality is that there's style to every one of these things. And I want to just say this. I think that I'm going to say this later on, but before I forget it, in your company, keep in mind, you're writing code for other people. You're not the primary audience, the code you write. First, the compiler. Second, other people. So companies should have a style guide of some kind that tells, that just dictates how you write your code, what the formatting is. If you're going to do C or C++, are you going to put the little bracket at the end of the first line and then drop it down, or are you going to bring it down like the old begin and end in Pascal? And the bottom line is it doesn't matter. Just pick one in your company, and this may be an exam question, but how are you going to solve the coding style wars? Answer: just pick one. And there are pros and cons to every single one of them. I've got my own opinions, but because typographically, so this is a true story. A few years ago, the Ensign changed their layout. I don't know how many of you are aware of this. The idea was they were going to a unified formatting and distribution. So in order to do that, they expanded the pages. English tends to be one of the more efficient languages. Of the natural languages, English is I don't know if it's the most efficient, but it's dang close. So other languages take more space to say the same things. So you have to, what they did with the English version was it moved from a fairly, reasonably compact typeface to white space between the lines, so that when you were doing a different language, you could fill it in. And they basically had, so they could do one layout of the entire magazine, translate all the articles, and then drop them into the same format space, and they would fit. I think it's a great approach. But there was actually a letter to the editor printed in the Ensign about somebody's like, I hate the new format. Okay, why do they hate the new format? There's nothing wrong with it. And the same thing happens if they ever change your newspaper, or if you go to pages that kind of violate your expectations. It's all about the fact that they have become accustomed, the brain acclimates to what it is looking like. That's why if you read a book and it's going to be in some fairly normal fonts, so there's going to be a fairly small set of fonts that you're going to find books written in. And if you pick up a book and it's all caps, or it's, I don't know, comic something, or, you have an entire book written like that, it will just be painful to read. The words are the same. What's the problem? And the only problem is that your brain has become acclimated to looking and seeing and expecting a certain kind of flow, and the brain just sets those kinds of it's like setting up their own little macros or something. So with your code, it's the same thing. If you expect to see a line of C with a bracket at the end, and the next thing you see is the next functional line, then your brain sets up an expectation to see that. If instead you see another bracket, another level, it costs you another level of indentation, as well when you do that, depending upon how you do it. Your brain just sets up these macros and comes to expect certain things. You reduce the time it takes you to comprehend code when everybody does it the same way, and you just get used to it. And even if you think you hate it, mostly you're just not used to it. Okay. So naming conventions is kind of part of that, right? So just check this out. How important, I equals I minus II, triple I equals Aretha plus sales tax, blah, 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 it's horrible. As opposed to say, I don't know, balance equals balance minus last payment. I mean, this, and you hit, and I've heard stories, and this is a recorded podcast lecture, so we don't have the stories. If we were all here together, we could share the stories, but I have heard things like a guy that worked with another guy who was either learning Spanish or had served a Spanish-speaking mission, who made all of his variable names random Spanish words. Horrible, atrocious. I think the guy worked for OIT. I'm not sure, here at BYU. I mean, just horrible. People who would like, everything's like A, B, C, D, you know, I just don't like typing all those letters, whatever. Keep in mind, you're not writing for yourself. You're writing for future generations of coders who have to read what you wrote and comprehend it. The biggest pain to software engineering, from a coding perspective, is trying to read what somebody else wrote and understand it. You have to build a mental model of what they created. And you've got to figure out how to lower the barrier for the person who comes behind you. And I've seen some, you know, code with great comments. Okay, this next part's a little tricky. I pulled my famous little stunt. I did this where I do the one thing and the one thing, and you can read it and go, oh. I remember the very first time at HP, actually, in the 80s, and it was assembly language, and I saw this little instruction where a particular register was XORed with itself, you know, and I kind of went, what is that doing? You know, why are we XORing a register with itself, you know? And I just kind of thought about it for just a second, and I'm like, oh, XORing anything with itself causes it to become 0. And it was faster from an instruction perspective, from a machine cycles perspective, than like moving a 0 or just assigning it to be a 0. You know? But again, and I had to then figure out and create a little macro in my head when I see XOR register with itself, that's how you zero stuff out. I had to get that little idiomatic pattern in my head. But until then, I was spending, you know, a couple minutes just kind of going, why are they doing that? You know? So it's just, you know, that was a situation where sometimes there's a vernacular. Like, for example, when you're going to do, if you're coding in C and you do a for loop, you're going to use I as the index. And if you have nested, you're going to go J and K. And, you know, that's not meaningful objectively, but everybody knows that, so you're okay. Or where P is a pointer and S is a string, and all that goes back to Kernahan and Ritchie in the original C book. Okay? But if it enters into the collective vernacular, fine. If you're trying to just, you know, call all of your variable names after your friends from Armenia, then you just should be taken out and flogged. Okay, so here's some other examples. I'm going to actually walk over here. So we got good names and bad names. We're looking, for example, at a running total of checks written to date. So, you know, good names might be running total. These are from McConnell, by the way. Check total, N checks. Bad names are like CHKTTL, all caps, CT, you know, which could be like a CAT scan, written, or X1, X2, even just checks. So this just persists. The same idea. Velocity of a bullet train, current date, lines per page, things like that. Anyway, and so why do we have naming conventions? You got multiple programmers. I mentioned all this already. Someone else has got to look at your code. The other interesting thing is your program is really big. If it gets big, you can't hold it in your own brain. And this is another common experience. I've heard this from multiple sources where somebody comes back to some code and they're just like, who is the moron that wrote this code? It's just horrible. And then they like go up to the top of the header comment. It was them. They hadn't even remembered writing it, let alone what was inside of it. So you might think, oh, there's no greater punishment than having to look at your own code like 2 years later. When you don't have the mental model in your head, then you realize how tough it is. Let's see. Yeah, in other words, you always have to employ decent naming conventions, okay? There is, in the case of Java, because of Sun, there's a coding style guide for Java, which if you're going to do Java coding, and I just throw that out as an example. In other environments, you got to come to grips with what the styles are going to be. And in this case, you got Sun helping you, but when it's something a little more organic, it's a little harder. And this doesn't really apply so much because we're not necessarily building any code in Java here, but there's another thing called Hungarian naming convention. Okay, I don't know if you're familiar with this. I really dislike it, like desperately, badly dislike it. You have a base type, so like WN for a window, str. So what it does is it creates, you know, one or more prefixes like array handle and a qualifier, And what you wind up with, let me walk over here. What you wind up with, like here, ICH, an index into an array of characters. You might think, okay, well, I just violated all of my principles. Well, not really, because this PACH is part of it becomes part of a shared vernacular. So you're not really breaking the rules, because you're supposed to be able to get some fluency and then figure this thing out. Here's my problem. My biggest problem with Hungarian notation. I got a pointer to an array of characters to insert. The problem is, what if I come back later and I decide I want to change the data structure of this thing? In a really decent modular design, suddenly, what if it's not a pointer to an array of characters, but it is a string or something, and I'm going to insert it? You know what I mean? Suddenly, I'm sticking too much information. I'm sticking too much. I know this seems ironic because we're in the code, but I'm sticking too much implementation detail onto the name. And in my mind, it hurts me when it's time to refactor. When I just realized, oh, I should have never used a pointer to an array of characters. There was this other solution I could have used. There was just object available to me or whatever. That to me is the big limitation. So I really dislike Hungarian names, but I want to throw that out for completeness. Names to avoid, misleading names and abbreviations like false. This stands for fig and almond season. Names with similar meanings, rec num and numrex. We've all done. I haven't done the false name. That's just really over the top. But this one here, I've done that one before, and then you get in there and you don't remember which one's which. Then what that leads to is logic errors, because you grab the one guy and you think it's the other one, and you use it, and then you've just trashed it, and your logic gets screwed up. Avoid variables with different meanings but similar name, like client reps and client recs. They mean different things. They're even different words, but avoid names that this might seem dumb, but even just names that sound familiar can create some confusion. Here's another one, second of 3. Numerals in the names, file 1, file 2. Now, I think that there are times when I know that I have 2 files, for example, where I think maybe file 1 and file 2 works. But it's still a little dangerous. Misspelled words like highlight, words that are commonly misspelled in English, like ascend, conceive, prefer, absence, accumulate. Don't differentiate based on capitalization, even when your language, is case sensitive. Fired, financial review document, full revenue dispersal. Again, every bit of this comes back to programmer cognition, the cost of looking at code you didn't write. Did I say you didn't write? Looking at code that you didn't write and creating in your own brain a mental model so you can then go in and tweak it without breaking stuff. That is the single biggest cost of software. And so everything you're doing here is just making that harder. Well, and not to mention the fact that you make it harder just to not get confused yourself. And here's the last one. Don't use, again, names totally unrelated. Let me come over here again. Hard to read characters, you don't really think about this one. Like 1 and L, you can get confused. You look at it and you get confused. 1 and I, period and comma, 0 and 0, capital O, I think so. 2 and Z, semicolon and colon, S and 5, G and 6. And then these are just some examples. Just look at these for a second. I think you can, even on the podcast, I think you can see this well enough. And I don't know in this case, yeah, it's just kind of giving an example where you can see how, at first glance, you go back and forth and you're just like, they look the same. Then you stop, you break it down a little bit, and you see, that this O and that O are different, that the 2 and the Z, et cetera, et cetera. So just kind of keep, this is all from McConnell again, from Code Complete. Okay, let's see. Yeah, we're actually almost done. So those are all from McConnell. So a little bit more about layout. Again, really it's all about comprehension. It's all about having the code be so readable that you can grasp as you're building it and not get yourself confused. And then when somebody else comes to read it, they can look at it and construct an appropriate mental model. That's almost what this is all about, this whole lecture. That to me is a really critical concept, and there ought to be something on the exam about that. Good visual layout reveals the logical structure of a program, okay? And that's what you're looking for, sufficient white space, sufficient layout. And this is Elliot Soloway, Kate Ehrlich. The results point out the fragility of programming expertise. Advanced programmers have strong expectations about what programs should look like. And when those expectations are violated in seemingly innocuous ways, their performance drops drastically. They did research on program comprehension. And I'll give you an example of this, not necessarily just coding style, but I think that it was Soloway and Ehrlich that did a study about beacons in the code. For example, if you look at some code and you see a swap, so for example, you see two things, A and B, and you take what's in A and you put it over here, and you move B over here, and you then take what's over in that spare little buffer and put it back in B. You see the swap. What does that trigger? What do you think of when you see that? Sorting. Turns out if you experienced programmer, they see that swap and they just go, sorting routine. They then did tests with engineers where they would stick them in front of code, and then they would take, just in the middle of nothing, they would take two pieces of whatever and they would throw the swap in there. Just a little piece of code that just swapped two variables. And it was not a sorting algorithm, and a huge chunk of the programmers, as soon as they saw the swap, they could not convince themselves that it wasn't a sorting routine. Because there's no other reason to do a swap between two variables, because you can use two variables and just use the one or use the other, but actually to exchange their contents is usually a swap. So that's an example. Now that's kind of a procedural thing, but what they're saying is that really what I was saying, when you look at the layout, you expect certain things, and it really slows you down when you're getting what you don't expect. So, so again, the layout should represent the structure of the code, improves readability, and withstands modification. Okay, so where you can make changes without killing the formatting. Here's an example. I'm just kind of simply saying, don't try this at home. There was an international, I don't know what the IOCCC.org. I think it was International Obfuscated C Code Competition. I think it's what it stands for. Basically, people wrote programs. They had to be functional, compilable, and runnable C programs. So, you know what I mean? You look at this, and it's a functional program that does something. But this is a little bit silly. And people get a kick out of that just for grins. But I've never seen anything this bad in professional code. But for all intents and purposes, you can do about the same thing. Okay, just two more slides. The next to the last one on commenting. So the different kinds of comments. One of them, the first one is you're just repeating what the code says. That's not that interesting, and there's no real value. So just don't do that. Okay. The first time I wrote an assembly code, they made us comment every line of the assembly code. So move 5 into the AX register. And what is my, move, AX comma 5. What's my comment say? Move 5 into the AX register. Meaningless. If I look at the code and the code already says what the comment says, if I just read the code, I'm not adding any value. Explanations belong there. Okay? If the code's tricky, well, the other principle is if the code's tricky, maybe you should be writing simpler code, but there may be reasons why you have to write tricky code. Another one is markers. You put little breadcrumbs. Fix this up later. This needs to be tighter. This is a workaround. This code in the comments is the real thing. This is a workaround. Just little markers or things. Summary of the code, like block comments, and description of the intent. You've got to have some ability to understand the programmer's original thinking in order to be successful. So the more you can do in your comments to communicate to the programmer that's going to come along and read your stuff, the better. And the very last slide in this lecture, self-documented code is really the goal. This is kind of the summary. Your goal is self-documentation, by which I mean your code is so well written, the variables say what they are, the layout is clean, the structure shows the hierarchy. True story, I forgot to share the story. I was a grad student at Oregon State. We were doing a project, it was like a user interface class, and we were doing we were doing two-person teams that shifted every week. So you got a new partner for the next chunk of stuff every single week. And I had a partner, he was from India. That's only relevant from an educational perspective because I asked him an interesting question. He was writing his part of our code, and he had a bug. And he's like, Chuck, I got a bug. So I come over there and I look, and we were writing in C, and his entire program, the entire program was left justified. You know, and I understand you're the guy writing it, but he had a bug he couldn't find. So I said, can I drive? Yeah, jump on the keyboard. First thing I did, I roll in, I start going, bip, 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 throw on white space, separation. Just start walking through his code. It was only like a couple hundred lines of code. From the top, I start moving, looking at the structure, and then indenting, you know, and pretty soon, and once I had the code structure indented appropriately, the logical error that he was seeing was immediately transparent. And he was like, oh, wow, you know, you're a genius. And so then I asked him, I'm like, you know, where you went to school in India, I mean, didn't they teach you to like write code with sufficient white space and indentation? And he's like, oh yeah, they always had us do that. You know, that was always required before we turned the program in. We always did that at the very end because we had to turn the program in, which was just stunning to me. I was blown away. Because then I kind of just tried to teach him this principle. I mean, by this point, I'd been a professional software engineer for a number of years, going back to get my PhD. But just this notion that you know, it's not for the teacher or the TA, it's for you and it's for the person that's going to come along behind you. If you're doing it really well, you yourself have an easier ability to comprehend what you're doing. So that's just an example. True story. You still need other documentation, especially depending upon what company you're working for. And this third bullet, huge. The single greatest cost of software development is maintenance. The single greatest cost of maintenance is program comprehension. And the single greatest part of program comprehension is read code you didn't write and figure out what it means and create a mental model in your own head of what it's doing. It's the same reason that in 428, the common thing with the persistent project that we do is for each generation to presume that all prior generations were idiots. Only because once they look at what they did, they don't get it. But guess what? Once you do what you've done and embody that, throw it out, the next generation is going to think you're an idiot because the comprehension problem is hard. Okay? And really, that's this last part. When you're making changes, the most difficult part is understanding the code before you make the change. You may spend days creating a mental model so you can make the 15-minute fix without breaking anything. And that's really the punchline. This has everything to do with program cognition and software maintenance. So you're not writing for yourself. And that wasn't too bad. Maybe an hour, a little more than an hour. 43 slides. But that's pretty much it for coding and implementation.